Hello, Honor Stats. We're now starting Chapter 4. This is Section 4.1, dealing with scatter diagrams and linear correlation. So our focus points. We are going to make a scatter diagram, which is a very straightforward process. We're going to visually estimate the location of the best fit line for a scatter diagram. We're going to use sample data to compute the sample correlation coefficient, which is denoted by the lowercase letter r, and we're going to investigate the meaning of that particular correlation coefficient. So first and foremost, a scatter diagram. A scatter diagram is a graph in which data pairs, x and y, just like in algebra when you plot a point, are plotted as individual points on a grid with a horizontal x-axis and a vertical y-axis. We call the x-axis the explanatory and the y-axis the response. The easy memorization is there's an x here, an explanatory, and it deals with the x-axis. So that's an easy way to remember those two. So the example we're going to use is this. Phosphorus is a chemical used in many household and industrial cleaning compounds. Unfortunately, phosphorus tends to find its way into surface water, where it can kill fish, plants, and other wetland creatures. Phosphorus reduction programs are required and monitored by the EPA. All right, so we're going to be dealing with phosphorus. A random sample of 8 sites in California wetlands gave the following information about phosphorus reduction in drainage water. In the study, X is the random variable that represents phosphorus concentration at the inlet of a passive biotreatment facility, and Y is the random variable that represents total phosphorus concentration at the outlet. Okay, so at the same time, we're going to do inlet and outlet and see what the phosphorus level is. So that's our two different variables. So we're going to make a scatter diagram for our data. This is our data. So you know how to read it. Remember, X was the inlet and Y was the outlet. The 5, 2, and the 3.3 go together. They're basically the point 5.2, comma 3.3. It's an ordered pair. So it's your job to look at the data pieces and figure out what should the range of your X and Y axis be. So you see the X's go 5, 6, 7s, and 8s. So that's why our x-axis is 5, 6, 7, and 8. Notice this little squiggly is needed because we did not start at 0. The Y's, we got 3s, 4s, 5s, 6s, and 7s. So that's why we go 3, 4, 5, 6, and 7 for the y-axis. Again, squiggle, squiggle, because this is not a true 0. So let's plot the point 5, 2, 3, 3. So over 5.2, up 3.3, that is this point right here. We'll do one more. Let's do that one right there. Over 7, up 6.1. That's all the way up here. That's this guy right there. So then we have all the other data pieces that we're going to plot. And what you're going to get is a scatter plot. I just wanted to erase everything on the scatter plot so you can look at it a little bit better. Now we're going to talk about what we call a best fit line. In so many words, you have to look at these dots and you have to draw a line, which is obviously this green line here, such that that green line touches as many points as it can, and there should be the same amount above and below. All right, so you're kind of centering it, I guess, such that it's in the middle of all of the dots in your scatter plot. Okay, it's called the line of best fit. And when we get to chapter 4.2, we're going to find a better technique, and we're going to actually find the exact line called a least squares line. Back here. We can draw many lines. That's good. So this is what I want you all to see right here. We can draw many lines in that figure, but in some sense, the best line should be the one that comes closest to each of the points of the scatter diagram. All right, let's continue. So to single out one line as the best fitting line, we must find a mathematical criterion for this line and a formula representing the line. But we're going to get more precise. So here's a couple guys that are scatter plots, but they're going to have no linear correlation because, like this one, you can throw a whole bunch of lines. All these lines would, in a sense, fit. This is not linear at all. Okay, it's curved. We call it sharply curved. So therefore, each of these would have no linear correlation. So if you think about correlation and a scatter plot, and they're dealing with lines, this would be a positive sloped line. This would be a negative slope line. If you look at both of them carefully, in a sense, let me erase this guy here. In a sense, this one is somewhat strong. They call it moderate. So this is positive and somewhat strong. This one is negative and somewhat strong. This is positive and very strong. We call it perfect linear because all the dots line up in an exact straight line. And this is a perfect negative linear correlation. Okay, so if the dots are spread out, it loses a little bit of strength. When the dots all line up in a straight line, it's perfectly strong. And we'll give you a number for that here. Back to these two. This one would consider to have an R correlation coefficient of exactly -1. It's perfect and it's negative. This would have an R of 1. So perfect straight line, the sample correlation R is going to give us a number for that. So when we go correlation coefficient, it has to be a number between -1 and +1. It can include 1 and it can include -1. Is going to be 1 or -1. If not, it's going to be a number in between. When R is 0, that's the one that says that there's no correlation. Okay, so as the numbers get bigger or closer to 1 and closer to -1, that's how it builds its strength. So something with a positive 0.94 would be pretty strong. Positive. 0.23 would be a weak positive. -0.974 would be a strong negative, and -0.31 would be a weak negative correlation. And these are all values of R. And what we're going to do now is we're going to see how we actually find the value of R. So development for our formula for R. This is the first formula they give us, and it's kind of ugly. Yeah, you know what n is. You know x is each term. X bar is the mean of all the x's, the y value, the mean. And then notice these s's are our standard deviations. So if you remember your last test, could you imagine computing a standard deviation, doing all those steps that we did before? You'd have to do 2 different charts. You would have to know the formula. This one's a little tough. So we gave you a little better. That's going to look ugly, but it's not as bad. Here is what we're going to do. Pinch this open so you can see it. Here are the 5 things that you're going to need. This one, I'm giving you all of the x pieces, so you're going to add them all together. Here's the sum of all the y pieces that I give you, all the data pieces. You're going to take all the x's and square them. You're going to take all the y's and square them. And then you're going to multiply the x and y together. Remember, x and y are partners. They're an ordered pair. And now look at this formula. I know it looks nasty, it looks bad, but it's not too bad. And you just count how many items there are. This is this last column right here. You already found it. This is the first column right here. This is the second column right here. So you've already done each of these pieces, so they're going to be easy for you to find. The denominator, you're going to have a big old square root here and a big old square root here. One's going to deal with the x's and one's going to deal with the y's. There's our n again. Here's the sum of all the x squares, which is this guy right there. And then we have to take the x's again, and we have to take this number and square it. Over here, there's our n again. Here's our y squared column, which is that guy. And then here's our y column, which is this guy here, which we have to square. Okay? So we'll show you all of this in chart form. And in the chart that I'm going to give you, there'll be 1, 2, 3, 4, 5 columns. This will be our x's. This will be our y's. This will be our x squares. This will be our y squares. And this is our x times y. You're going to put all the numbers in each of these columns. And then you're going to take the sum of each of them. And we're going to use these in this formula. So here's our example. A test site at the Great Sand Dunes National Monument gave the following information about x and y. I guess I didn't have the other one. X is wind speed and y is the rate of the sand when it forms a sand dune. Okay, so here's the values, whether we need the words or not. But know that this is the ordered pair, 70, 3. This is 115, 45, and so on. These numbers here. These numbers range from 70 to 125. These numbers range from 3 to 62. One, just so you know. Let's find 105, 21. So we're going to collect the data. You can now see what I meant by the wind velocity and the drift rate of the sand. So wind velocity, wind speed is x, the drift rate of the sand. Here are the values that they used for the first numbers x. Here are the values for the y's. And those came from, just so you know, so notice the 3 is included, and this goes up to 60. This is 70 through 130. Each of those dots are your scatter plot. Okay, let's do over 105, up 21. That's that guy right there. Okay, so we plot all 7 of those points. The blue guy is our line or best fitting line. They just drew it in there. They're trying to get it smack dead in the middle of all of those dots. And remember again, in the next chapter, we're actually going to find the exact way to get the equation of that line. All you're doing is drawing it in by hand. Now, if you draw here, we obviously have a problem. You're trying to find the line that fits the best. Notice this line here, the one they chose, it's pretty close to all of the dots. I thought it was. All right, so here we go. I told you that we are going to find 5 columns. We're going to write down all of our x's, write down all of our y's. Remember that first point was 70 and 3? They go together. 70 squared is that. 3 squared is 9. 70 times 3 is 210. So we're doing x, y, x squared, and xy. I'll do one more. 88 is our point that I gave you. 12 is the point that I gave you. 88 squared is 7744. 12 squared is 144. 88 times 12 is 1056. So it's your job to take the sets of data that I gave you, square the x's, square the y's, multiply x and y. These are going to be the important numbers. We're going to go red here. 678, that's the sum of the x's. 166 is the sum of the y's. 67, 80, 892 is the sum of the x squares. 67, 68 are the sum of the y squares. And the sum of the x times y is 18,458. Is 18,450. The sum of x, 678. The sum of y, 160. Sum of our x squares is the 67,890. So the sum of the x's is this guy again. which is this number here, squared. The sum of our y's being squared graph from this here. So here's our formula. N is 7. The sum of x times y, 8. That's where this came from. Then we put a subtraction sign. We have the sum of x times the sum of y, 6. 678, 166. So the numerators are done. In the denominator, we have our n, there's our 7. We have the sum of our x, 2. That's why it goes right there. Subtraction sign. And now we have to take the sum of the x's and we have to square that old number. And we have to square it, 678. All underneath a radical symbol. Now we have the next radical symbol. There's our n, right? N. Then we have our sum of our y squared, 67, 68, subtraction sign. And then we have our y's, that's the 166 squared. Okay? I do not like how the book did this. Okay? So, I want to kind of explain what I want you to do here. Once you get to this step here, go ahead and do this work up top in the numerator, and you'll get the 16,658. But for the denominators, I want you to do this work separately. So 7 times 67,892, hit equals, then hit a subtraction sign, and hit 678 squared. That gives me 15,560. The other guy is 7 times 67, 68, and we're subtracting 166 squared. That gives me 19,820. Okay? Now, the reason I don't like this is because they typed this into their calculator and rounded. They typed this into the calculator and rounded. And then they rounded the answer. So to me, they've rounded 3 times within a problem. I think you can plug all of this into your calculator at once. When you do so, you don't have to physically multiply the 15,560 times the 19,820. Just type it in your calculator. So I'm going to type in 16,658, hit a division, hit my square root, hit a parenthesis under the square root, and then type in the 15560 times the 19,820, close the parenthesis and hit enter, and it'll give you the 0.9485, so it's 9. I know we got the same answer, but sometimes you may be off by that thousandths of a decimal if you round within the problem and don't do it the way I did it. So, think about what I gave you before. The R is a number between 1 and -1. This being the strongest positive, this being the strongest negative. This is a positive 9.49. That is a pretty strong positive correlation. And if you, but that 9.949, and we're going to memorize this big nasty formula. We're going to plug our numbers in. We're going to hit enter, and it's going to give you a value for R. All right, and then we're going to obviously is exact. So our interpretation, what does that R tell you? Since R is very close to 1 and obviously positive, we have an indication of a strong positive linear correlation between wind velocity and drift rate of sand. In other words, we expect the higher wind speeds tend to mean greater drift rates, right? Because it's positive and positive. Ladies and gentlemen, is chapter 4.1. You should be able to take a set of bivariate data, that's what they're called because they're 2 data pieces, construct a scatter plot, a scatter diagram, by writing an x-axis and make sure you label it correctly, writing a y-axis, label it correctly, and putting a dot on those axes for each data point. Then you're going to draw with your eyeballs what you think is the best fitting line. It should touch as many dots as possible within your scatter diagram. From there, we're going to actually find the true correlation coefficient R. We're going to find x, y, x squared, y squared, and x times y. We're going to find all their sums. We're going to memorize that big, nasty, long form. Talk about it by saying how strong or how weak it is because of the R. All right, you guys, we're done with 4.1. All right, so this